Good evening. On behalf of the Indiana University College of Arts and Sciences, I would like to thank you for joining us tonight. I'm Vanessa Clow, and I serve as the college's Director of Alumni Relations. Our Food for Thought live streaming series serves as an opportunity for our alumni and friends to hear from faculty experts, explore topics of interest, and stay connected with IU and the College of Arts and Sciences, regardless of your location. At this time, I'm delighted to introduce tonight's featured presenter, College of Arts and Sciences Executive Dean and Professor of Physics, Rick Van Kooten. Since arriving at IU in 1993, Dean Van Kooten has served as chair of the Department of Physics and as vice provost for research, working across the campus as a passionate advocate for scholarly activity. He earned his PhD in physics from Stanford University and began his career as a scientific associate at the European Laboratory for Particle Physics, CERN. He has co-authored more than 750 publications, most in the area of particle physics. As both scientist and administrator, Dean Van Kooten is an experienced collaborator, having guided the research directions as physics coordinator of large international collaborations of hundreds of researchers. In his role as the college's executive dean, he remains firmly committed to the importance of a liberal arts education in the College of Arts and Sciences, both for its inherent value and for building the foundational skills of creative, collaborative, and critical thinking in communication. Following his presentation, Dean Van Kooten will be joined by Provost Professor Jeffrey Zaleski for the audience Q&A session. Professor Zaleski, who has served on the IU Bloomington faculty since 1996, researches the fields of metals and medicine, bio-inorganic chemistry, and synthetic chemistry and materials. As the former vice provost and associate vice president for research, Zaleski is credited for playing a critical role in the development of a robust campus COVID-19 testing laboratory through the expansion of the Center for Genomics and Bioinformatics. You can submit your questions at any point during this evening's discussion. Simply click on the Q&A tab located in your webinar toolbar. Hover your mouse over the screen and your toolbar should appear. If you are unable to access the Q&A button, you may write Professor Zaleski directly with your questions. I will include his email address in the chat shortly. Now, it is my pleasure to welcome Dean Van Kooten for his presentation. Thank you.
Well, good evening, everybody. Thank you very much for joining me and giving me the opportunity to talk a little bit about my own research interests. I'm an experimental particle physicist, and I'll be talking about a result which is not so recent. It's been updated as a much better measurement since we first did it. But it's very, very much an area of one of the great questions in physics that I'll be talking about. And it's something that is still being explored now, and actually something that other faculty in the Department of Physics will be doing in a completely different way to look at this, to probe this tiny difference between matter and antimatter. But just starting things off, because we're looking at a tiny difference between matter and antimatter, first we have to determine or learn what antimatter is. So starting off with the most commonly known particles, the electron and the proton, is that for every matter particle, there exists an antiparticle, and that's what we call antimatter. So we have electrons, which are negatively charged, just that's the electric charge. We have anti-electrons. The only difference between these is the charge. So it's essentially a positively charged electron. So in fact, we don't really call it an anti-electron, we call it a positron for a positively charged electron, essentially. It has a positive electric charge. They both have the same mass. And for a lot of physics, they're treated identically, but they have other properties we'll talk about in a second. Now, when we look about the differences between matter and antimatter, often we're looking at what we're calling symmetries that we'll introduce later. So we have this operation, which just means this is C. It's a fancy word for something called charge conjugation. You don't have to worry yourself about that. What charge conjugation does, it flips the electric charge and it turns a particle into an antiparticle, in this case, the positron. And then you can do it the other way around as well. You can convert, essentially it flips a antiparticle to a particle. Now, like I was saying before, the physics remains the same. For example, I could take an electron and bounce it off another electron, and the force and how they distribute how everything acts is identical that if I take a positron and bounce it off another positron or other particles. So everything stays the same in that respect. The electromagnetic force, gravity, which I'll talk about in a second, also behave the same. So the next most commonly known particle is a proton. Is that a proton and electron make up a hydrogen atom. So for protons, we also have antiprotons. A proton is positively charged. An antiproton, again, the same thing, the exact same mass, but now has a negative charge, and they have the same mass. In fact, physicists now routinely make positrons, they make antiprotons, and they actually put the antiprotons and anti-electrons together, the positrons, to make an anti-hydrogen atom. And in fact, they're testing how a particle behaves in gravity. A very common question is like, do antiparticles fall up? No, if they have the same mass, they should fall down. But of course, this is something as scientists, we always want to check very carefully. So they're making anti-hydrogen atoms and looking to see how they fall in a gravitational field. Full disclosure, actually, protons actually are built out of other particles called quarks. A proton is two up quarks and a down quark glued together by particles called gluons, literally, because they glue the particles together. Antiprotons are three antiquarks. From this point on, you really don't have to know that much more about quarks. We can just talk about antimatter in general. So now, this is an amusing cartoon. First of all, the Far Side and Gary Larson, he's beloved by scientists because he actually has a lot of his strips or his panels had to do with science, and they're always very entertaining. Now, in reference to this cartoon, E equals mc squared. This is going to be the only formula in this whole talk, and it's probably the only physics formula that a good number of people in the world know that they remember, say, from their physics classes, that they had physics classes. So E equals mc squared. And we're going to talk about this is very, very important for everything we do in particle physics. So of course, E is energy, M is mass, and C is the speed of light, which is huge, essentially 300 million meters per second. And then you square it. So this is a gigantic number. And if you put it in the right units, so if you have a tiny little bit of mass can be converted into energy, and you can go back and forth, converting between mass and energy back and forth. And that's important. And it predicts how much is that the other property of antiparticles or antimatter is if there is a antiparticle, it would annihilate with a particle. So a very dramatic term, annihilation. And now we have a formula. If we have these two masses and convert it complete to energy, we can calculate exactly how much energy this is. So we can go this way, mass into energy via an annihilation. And then when we produce it, we can take energy and produce a particle and antiparticle. And they always come in pairs like this. There's something called baryon number, and it's got to be conserved. Again, we don't have to go into that detail. Just remember that you always have to, whenever you make an antiparticle, it always comes with its particle pair. And actually, this is the way we also make antiparticles. We can, in fact, take a lot of energy. We take a beam of protons, slam it into a fixed target, and then if you have enough energy, you can make particle-antiparticle pairs. Some of those will be antiprotons, and then you can do experiments with your antiprotons. Now, if you saw or read the book of Angels and Demons, I love the tagline in here. Before the Da Vinci Code was broken, the world lay at the mercy of angels and demons. This is actually in this case, the villain had a 1/4 gram of antiprotons stored in a magnetic bottle and was threatening to actually destroy Rome by exposing this just to air, just breaking the bottle open. And a very entertaining movie. And this is actually sitting in a car seat. Now, actually, first of all, it is, in fact, it is done where you can store antiprotons because they have charge. You can store them using magnetic and electric fields in the magnetic bottle like this. From this 1/4 gram, you can use that formula and E equals mc squared, plug in all the numbers, and indeed, if this amount of antiprotons was exposed to the molecules, nitrogen and oxygen molecules in the air, it would cause enough energy that's easily is the level of a nuclear explosion, and that would level Rome for sure. But you don't have to worry about this, is that the Fermilab Tevatron, which is no longer operating at Fermilab outside of Chicago, was the world's largest producer of stored antiprotons. They had a proton and an antiproton beam, And to make the antiproton beam, they had to make and collect them all. They only created and stored about 1 nanogram a year. And if it just remind you what nano means, that means it would take 1 billion years using this kind of process to actually get a gram of antimatter. So you don't really have to worry about it. And a magnetic bottle like this, you wouldn't be able to put it on a car seat. It's actually, they're much larger in real life than what they're shown here. Okay, so now we have the pair production and annihilation, and let's focus on here the pair production. Now, right after the big, when the Big Bang happened, there was a huge amount of energy. And out of those energy, you can make particles and antiparticles. Like again, gigantic numbers of particles and antiparticles. But because of this phenomena that for every particle comes an antiparticle, there should be equal amounts of particles and antiparticles. When we look at the universe right now, most of essentially the vast majority of the observable universe, it's almost all matter. In fact, there's experiments to talk about in a second that look for antimatter in the universe. So how do we, again, a big part of science is how do we know? Now, how do we know that the universe is mostly matter? Jim Musser is a physics professor and also was the executive associate dean and one of the associate deans in the college in the physics department. Although he's done experiments not necessarily looking for the antiparticles, he's done balloon flights where they loft a detector up above in the atmosphere in the Antarctic, looking for cosmic rays and sort of properties of the cosmic rays. You can also look for antimatter particles in those cosmic rays. The best bounds of antimatter coming in as cosmic rays from the universe is actually this AMS-2 detector that's literally bolted on the outside of the International Space Station that's been sitting there for a number of years looking for these antiparticles. Another one, and this is an image from the James Webb Telescope, and this in itself, you should get somebody from the astronomy department. You could probably talk easily for an hour of everything in this photo, including these little arcs, which are fragments of Einstein rings. They're not optical distortions. They're actually the gravity of galaxies bending the light of galaxies further past them into a ring. And I think even just about 2 weeks ago, James Webb collected actually a galaxy with a perfect Einstein ring around it. Really remarkable. But the question is, can some of these galaxies be all antimatter particles? And actually, because the physics acts the same, that could be true. But if you have chunks of the universe that are antimatter, even in interstellar space where there isn't very much material, there's enough that there be annihilation of that matter with antimatter, and you'd be seeing the photons essentially. And because we look at the distortions of the radiation coming from the universe, we know that essentially everything that we can see is made out of matter. So now we're trying to understand this current asymmetry between matter and antimatter in the universe. Where did all the antimatter go? And what are the differences between matter and antimatter? So we're going to talk about symmetries now, and that's the title referred to mirrors. And in this case, this is essentially a mirror symmetry for this tree, and here's an asymmetric tree. We can look at other symmetries. And so the first use of a mirror here also addresses a property of particles that we haven't talked about yet. Particles have mass, they have lifetimes, they also have spin. And it's essentially the smallest amount of angular momentum something can have, the quantized angular momentum. But essentially particles have, you can think of them classically as spinning like little tops. Now, if you have a particle that's moving this way and it spins in this direction, if you look in the mirror, it flips actually orientation of the spin. And that's actually called a form of what we call a parity transformation. So it takes a particle which is left-handed, and to get these handedness, for example, you can try this, you can look like a physicist when you do this, because you do this in physics class all the time. You stick your thumb in the direction of motion, and your fingers around the orientation of the spin. Your right hand gets the right orientation there, and the one on the left has your left hand. So this is something, again, that we look for is physics difference between particles that are spinning left-handed or right-handed. And now for things like the electromagnetic force, no, that's fine. Gravity doesn't care about spin. Something called the strong force that binds quarks inside of particles, it doesn't care about the spin of particles. Something that really cares about the spin is something called the weak force, which is responsible for radioactive decay. It's responsible for the fusion reaction that happens in the sun that keeps us alive. So it's a very important force, but it's not symmetric for the weak force. Now, so we have this parity between like a mirror between left-handed and right-handed particles. We have something we all just learned where we can flip the charge or changing a particle to an antiparticle. If you do both of them, or you do these sequentially, if you change a left-handed particle into a right-handed antiparticle, for a long time, well, not for a long time, initially, we thought that this is a perfect symmetry. You know, for the observation we saw, we said that this is true, that physics looked like it was the same when we did both the charge and the parity flip. And again, we're looking for the properties of physics. But when we did experiments, we find it's not. It's almost perfect, but there's tiny differences. And this is where it's not symmetric. We call this CP violation. It's a violation of the symmetry. And this CP violation, or this not perfect, is that crack in the mirror that I referred to in the title of the talk. Now we're all ready to sort of address what happened at the early universe to get where we are right now. So at the early universe, the first 10 to the minus 35 seconds after the Big Bang, this is a mind-boggling tiny amount of time. The number of particles would equal the number of antiparticles, like after all the energy of the Big Bang, going to the creation of the particles and antiparticles. But then, due to the CP violating processes between the difference between matter and antimatter, that for every roughly 10 billion antimatter particles, there was 10 billion and one ordinary particles. And as the early universe was just a soup of quarks and gluons flying around and photons. As things cooled down, then there was a great annihilation, is that these would almost all completely annihilate each other except for that one. They would just essentially cancel each other out. This is kind of like the last person standing, and this one is us. So this is a very existential thing, is that we wouldn't be here today if it wasn't for this tiny symmetry between the matter and antimatter. Not really us in terms of our bodies, but really the visible universe. And so actually a way to do this with an experiment is actually using these two processes, pair production and annihilation, as one way we do our particle physics. So we can just combine them. Here we have annihilation, we have an electron, an anti-electron or a positron. They come together, annihilate, you have energy, and then you can get another positron and electron coming out. Now, this is called the Feynman diagram in honor of Richard Feynman, and particle physicists use these all the time. In fact, use them as a calculational tool, but also used to sketch things out. This is like the bread and butter of particle physics, these Feynman diagrams. This is like one of the easiest ones you can draw, and for a process that happens in particle physics. What you can do is that you can accelerate in these gigantic colliders, positrons, billions of positrons at the same time, billions of electrons, and put them in rings, have them circulate, and you make beams out of them, and you collide the positron beam with the electron beam. And you do this and because these have more energy, when they annihilate, there's more energy in this process right here. You just go equals mc squared, but you take into account the energy coming in of these particles. And then when you do that, you can make more massive particles. Again, E equals mc squared. If I have larger energy, I can make larger masses, larger particles here. And we do this all the time. So in fact, this was done at a project that Indiana University worked on called the Large Electron Positron Project over at the European Laboratory for Particle Physics. And then something we worked on as well was at Fermilab, same thing. Protons, you accelerate, antiprotons, you accelerate, you collide them with lots of energy and you make massive particles. Now, these massive particles, in this case, would be these particles that are called B mesons. Is that there's actually, I talked about up and down quarks, there's really 6 quarks. This particle right here is a B quark or a beauty quark or a bottom quark combined with a down quark, and this is a B quark with a strange quark. Now these are weird particles in that there's some quantum mechanical process where when these are flying along, the quarks inside go from quark to antiquark back, and then the whole particle turns from particle to antiparticle, particle to antiparticle as it's flying along before it decays. And then we just look at the tiny difference between if it starts off as a particle or if it starts off as an antiparticle. This is at Fermilab outside of Chicago. This is the main office building. Most of the experiments are done in much less aesthetically pleasing buildings as this. And this is actually the cooling pond beside the building. We build detectors. Part of this detector, this is the D0 detector. This is an older generation detector. I have my backup slides. I can show the next generation detectors much larger. Here's a person for scale. The current generation detectors, for example, the Atlas detector that IU physicists work on is many times larger than this. Protons in one direction, antiprotons the other direction, and they collide at the center. And then we have instrumentation that sort of tracks the particles that come flying out. This is a side view of the collision at where the protons and antiprotons collide here. This is a crossway view, and then this is zoomed up. And then just to appreciate the scale, this is a millimeter. From here to here is a millimeter. In this case, is a reconstruction of this particle that we call the B sub S meson. That was created here, got to this point, and then decayed. So a fraction of a millimeter. In this time, it turned into a particle, antiparticle, and then back to a particle in this kind of distance. So these particles only live, they have a lifetime of 1.5 trillionth of a second. So luckily they're coming out at essentially the speed, very close to the speed of light. So they actually have a measurable distance, so we can measure them and then see if it's a particle, antiparticle, or when it actually decays. Again, don't worry too much about the details of this. It just gives you a sense of the scale and how we do this physics. Now, the observation at that point didn't agree with predictions, and it was like 1 chance in 10,000 that it was a statistical fluctuation. But it looks like that was a statistical fluctuation. We look at enough things that happened, and this is what science is. It generated a lot of interest and a lot of theoretical papers trying to explain why this had more CP violation than we thought. But even this measurement and all the measurements we've seen so far involving, in this case, quarks, are not enough to explain that matter and antimatter asymmetry, which is required to give us the amount of matter that we see in the universe today. So there's some missing source of CP violation, or this, again, cracked mirror in one of the forces. So we have to look for CP violation somewhere else. And this is something that, again, IU physicists are working on. And now and like I said, that experiment that I showed with that result has now been updated. In fact, even in the winter conferences, there is like a measurement of the largest CP violation observed in quarks ever. And that is, again, still not enough to explain the matter-antimatter asymmetry in the universe. Now physicists are looking at neutrinos. In fact, this is, there's a group in the physics department that does a lot of neutrino work. And there you just compare neutrinos to antineutrinos. This is an experiment where neutrinos are created at Fermilab here, and neutrinos can easily travel through the Earth. They interact very weakly. So you have to send trillions and trillions and trillions of them through the Earth. And then there's a detector in Ash River, which is essentially a big rectangle of ultra pure mineral oil. Then when a neutrino comes in, here's an event, nothing, because the neutrinos don't have any charge. And then it interacts. This thing is 70 meters long. So then it's like 20 meters high, or 20 or 30 meters high, and then same thing, other dimension. So it's almost the size of a football field, that length, of looking for these interactions and then comparing neutrinos to antineutrinos. This is something like a $250 million project, and faculty member Mark Messier in the physics department was a longtime co-spokesman, somebody else right now, but he did this for essentially through the construction phase and the initial running period of the experiment. Another one, and again, this didn't give enough statistics to make a really good test of CP violation. The next one is an even larger experiment called DUNE, or Deep Underground Neutrino Experiment, where again, at Fermilab, you use protons, smack into a target, you make pions that decay into neutrinos, and you shoot them down into a mine in South Dakota. I think this is actually a gold mine. And then large underground particle detectors, liquid argon, actually big caverns of liquid argon, and then looked at with very sensitive light detection elements to see when a neutrino interacts and leaves charged particles. So 800 miles away. So again, a number of faculty in the physics department looking at that. So what we're doing, again, is looking for cracks in the mirror. And how much bigger is that crack in the mirror? And it's almost guaranteed to be new physics, or what we call the standard model that we've been using that making all these predictions. Things are agreeing with the prediction, but there has to be some crack to explain our matter-antimatter asymmetry. So with that, I hope you've enjoyed this sort of insights into antimatter, antiparticles, and maybe get a sense of like why I find this interesting. It sounds like a very esoteric experiment or measurement one makes, but it's truly existential. What it is trying to explain is essentially this tiny symmetry between matter and antimatter that essentially results in where we are today. So with that, thank you very much for your attention, and I welcome questions.
Wow, Rick, that was really incredible, very thought-provoking, wide-ranging, and all I have to say is so many questions in so little time. So we actually got a question very early on in your talk, and it's probably one of the most fundamental that could be asked, so we're going to go to that right away. So the question is, why does the lack of perfect symmetry lead to more matter than antimatter in those first moments?
Okay, so if that was a perfect symmetry, and I should have said this, if there was a perfect symmetry there, all those particles would have annihilated with all the antiparticles. And the universe would just be a boring bath of photons, essentially. There'd be no matter to make galaxies, no matter to make planets, no matter to make anything. So it's that tiny symmetry that's left over that creates that results in the matter that we have today.
Okay, so I'm going to follow that up a little bit. Yep. So symmetry sounds a bit ethereal, right? And so, as what I'll call a lower profile chemist than a physicist, when I think of conversion between two species, I think of words like equilibrium and kinetics and things like that. So I guess my question is could this simply be a matter of the kinetics for conversion in one direction being different than conversion in the other direction? So right. That would be that's actually that when I say CP violating processes, it could be that. That's where it comes in, is it going one way and the other results in more particles than antiparticles, because it's actually at some point, first it starts out of equilibrium, but like there are particles that are being produced and then they annihilate, then they get produced, they get annihilating. And so it's actually in that, again, the equilibrium going back and forth that you generate the symmetry. So is there some kind of force that may stabilize matter versus antimatter?
No.
Or changes that equilibrium?
No, it's just like again, the CP violating component comes in what's called the weak force. Again, the force that drives how the sun works and also radioactive decay. It's an existing force that we have right now.
Okay, so we've got lots of questions from the audience. So how do you show the existence of antiparticles? Is it from the observations of energy produced or lost in the interactions?
No, that's actually that's the way that neutrinos were discovered, is that something was missing. Antiparticles are charged so that they're just as easy to see. It's just as easy to see an antiproton in a detector as it is a proton. The problem is you have to have a great vacuum, or else the antiproton will be annihilated in the oxygen and nitrogen molecules in the air or whatever is leaking into the vacuum. But you can track it. Is it what you can just see? You can see the annihilation. Is it you can actually watch annihilations and see flashes of the radiation coming from them. In that case, those wiggly yellow things, if they're just at rest and matter touches antimatter, you just get two back-to-back photons, and you can measure those.
Great. So in the early universe, were there antibosons, or was the annihilation of particles virtually all quark-driven before cooling could allow them to become greater particles?
Yeah, that's a really good question. If you notice, like right at the beginning of the talk, I was saying that for every matter particle, there's an antimatter particle. That the bosons, things like photons, there aren't antiphotons, for example. Photons, in what we call the standard model that we have, they're different. They don't have an antiparticle partner because they carry the force. They're actually not the building blocks of matter. They carry the force. Photons carry the electromagnetic force. Gluons carry the strong force. Things called W and Z bosons carry the weak force. And then what we think, what we call gravitons are potentially carrying the gravitational force, but we don't have a good quantum theory of gravity yet.
Is the amount of antimatter critical to the question of whether the universe will eventually collapse or expand forever?
No, it's that that's more of a question of how much mass is in it right now. So what I didn't mention is the fact there's something called dark matter that's in the universe. So we don't know what it is. Is that we have this weird dichotomy of, we have the standard model, which is a mind-bogglingly good theory, but it only describes a small fraction of the universe, the regular particles. CP violation might come from those dark matter particles, we're not sure, but it's the total amount of mass. It doesn't care whether it's matter or an antimatter, it's just the mass of the universe, which and sort of like the dynamics of the evolution, whether it's going to collapse or go on forever, expand forever.
So sort of a close follow-up to that, would you explain how the inflationary universe plays into this asymmetry?
I honestly, I don't have enough background in inflationary cosmology to answer that question. It's just like the universe just quickly expanded, but that was in space. Like, well, I mean, not in sort of space itself expanded very quickly in that inflationary process. It would have to do, what it does, in fact, is the dynamics, the cooling down in the universe, right? If the particles are being separated very very it's like it has to do with the cooling. I admit to not knowing enough about inflation and coupled with the CP asymmetry to answer that question.
Okay, fair enough. So I think you can handle this one. Could dark matter and dark energy have anything to do with this asymmetry?
Yeah, it could. It could. Dark matter is, well, we believe it's actually particles. And there could be some process in there that's caused by the dark matter. Dark energy is not necessarily, particles. Again, it's more the dynamics of the universe. It's sort of thing as we're seeing that as it gets less dense, the pressure increases, which is completely backwards. It's like negative pressure, and that's what's driving the expansion of the universe much faster. So I don't think dark energy could be it, but it could be the dark matter component.
Yeah, that kind of was what I was getting at about the equilibrium issue. Is there something out there that's changing the distribution? And so that goes to the next question. Again, pushing on this point, why more matter than antimatter? Why not more antimatter than matter? We understand why numbers are not equal, but why is that?
Right. It could have been the other way around. We could easily have an antimatter universe. It could be flipped, and then things would be fine. Literally, is that it could have been the other way around, and there might, if we have multiverses, there could be a whole universe which is an anti-universe made out of antimatter. You can do that, but then everything has to be antimatter. And again, the same thing. It'd be it'd be almost all antimatter with tiny bits of matter in it. That would still work exactly fine. And that has to do with that, the symmetry in the charge symmetry.
I'd love to know what an anti-car looks like, but anyway.
Yeah, just don't let it touch a car.
Right, exactly. This may be more of an astronomy question, but are Einstein rings the same thing as a gravitational lens?
Oh, those are exactly the same. That's a different name for gravitational lensing. Although you can have strong and weak gravitational lensing, the Einstein rings are essentially the galaxy in front of another galaxy behind it, just bending the light to make a ring or these arcs that you see. But it's gravitational lensing.
And when you get that phenomena, what happens to things like redshifts of the light? Is it distorted from other redshifts of other stars?
That's a good question. I don't know.
Okay.
I'll ask an astronomy friend, or if there's an astronomer out there, you can type it into the answer, the Q&A piece with an answer.
So what's the longest observed and measured time that an antiparticle has survived prior to annihilation? That's a great question.
Yeah. And it's something that I looked up for the purpose of this talk. I believe it's they kept antiprotons in a trap. We don't really call them bottles, we call them magnetic traps. 400 days. And it's like a collection. It's a number of antiprotons. One of the limiting factors is how good a vacuum you can have, right? That needs like an ultra good vacuum. But you can just keep it, just keep it away from matter, and you can keep antiprotons as long as as protons. That actually is an interesting thing. Like, we have a limit on how long protons live before they decay. We've never seen a proton decay. The question is does it behave the same for antiprotons? In fact, that 400 days is like one of the best limits, I believe, on sort of like the lifetime of the antiproton.
I think in the movie, it was either a battery that led to the vacuum or a battery that led to the field that was decaying. Yeah, that was decaying, right? That was going to cause the annihilation ultimately.
Yeah, again, to run something like that on batteries is not very
right. Okay, in recent months, we seem to have seen more popular science articles questioning the standard model because they say we found no dark matter, no dark energy. Also, some energy pattern we need to see hasn't been found. And the mathematicians, too, are growing skeptical, it seems. So what's your position on that?
What was the first one? The skeptical of the standard model?
Yeah.
Oh, okay. So the standard model is not, we know for sure, we know 100% the standard model is not the last word. It's not, there are imperfections standard model, or the standard model is a subset of something much larger. The same way is like, you can explain the whole world out with Newtonian mechanics, like just, F equals ma, all that stuff. You don't really need special relativity until you get to incredibly high velocities and energies. So the Newtonian physics was perfectly fine. And actually, you calculate everything with Newtonian mechanics. You don't need special relativity. We may be in that kind of state. The standard model just describes like some low energy subset of the universe that we're looking at today. And something beyond it, like a larger theory, they talk about grand unified theories, supersymmetry, things like that, where again, the standard model is a subset of it. We know 100% the standard model doesn't describe everything. So in fact, a good issue is that if the dark matter are particles, the standard model doesn't have a particle that fits, right? The standard model describes, 6 quarks, 3 charged leptons, 3 new types of neutrinos. It doesn't have the particles that you need for dark matter. So it's got to be something else outside the standard model.
Got it. Great. So what type of measurements can you make on this antimatter that lives for so long without destroying?
Oh, yeah, no. So that's actually that. And so very good ones are the antihydrogen. That's why they really wanted to build an antihydrogen atom, because in hydrogen are very famous. When the electron goes around quantum mechanically, you can get splits when the electron is in different states. It's called the 20 centimeter line. You can measure transitions in a hydrogen atom and then do the same measurement in the anti-hydrogen atoms to see if they're the same. And so that, there's experiments actually at the European Laboratory for Particle Physics. That's the main location for them, because they have a facility that makes antiprotons, decelerates them. That's a problem. When you make them, they're moving way too fast to do something with them. You have to slow them down. And so they decelerate them, and then, do other methods to cool them off even more. When we say cooling them off, that means just slowing them down and then stick them into like a magnetic bottle, and then, hit them with lasers and things to drive these transitions to see, is it the same between hydrogen as is between antihydrogen?
So along those lines, if you could make antiprotons and anti-atoms, you could make things like anti-materials, right? So if you made it, yeah, right. So let's even get less realistic. If you made anti-material in a matter world, what kind of properties could it have?
That's the thing is that it according to this symmetry between matter and antimatter, aside from the CP piece of it, it would act just very much the same.
Except for the annihilation problem.
As long as it lived in a vacuum and didn't encounter any matter, it's all identical. Your anti-car would work identical to a car.
Okay.
Just you have to check it, you have to make sure that anti-mechanics work on it.
Right. Yeah, because if a mechanic touched it.
Right.
So when you talk about this matter and antimatter at the beginning of the universe, it brings up the sort of comparison in the question to sort of the Higgs boson, right? So the God particle and the initiation of all particles, et cetera, et cetera. So can you talk a little bit about the two of them and how they compare and contrast and where the whole Higgs model fits in with the matter and antimatter?
Sure. Here, let's, can I get my slides back? So to talk about the Higgs boson, you want to go over to CERN. And this is what it looks like. In fact, this is 27 kilometers around the ring, and it's just a ring of superconducting magnets. And this is where the Large Electron Positron project was that the Indiana University also worked on. Then at Fermilab, and then they turned this into colliding electrons and positrons to colliding protons and protons, not antiprotons. And the reason for that is complicated, but if you don't have to make antiprotons, don't, because it's hard. And then that is actually 100 meters underground, has close to 10,000 superconducting magnets. They run at 1.9 degrees Kelvin. And if you just look at interstellar space, essentially the universe is at 2.7 degrees Kelvin. So if we're the only civilization, this may be the largest, coldest thing in the universe, because all these superconducting magnets added together, colder than actually interstellar space. And then the detector. So this is the next generation detector, because I wanted to really show this. So I showed, to scale the person, these are the people here on this. So it's like 44 meters, like half a football field, and 25 meters in diameter. So it's just huge. And then this is what a Higgs boson event would look like in that detector. These are, again, these are tens of meters. Each of these is the world's largest superconducting magnet. It has fields of Teslas. It essentially has the field strength of an MRI machine. And then the Higgs boson decaying into other particles, these two red and two green tracks. Okay, but what I did want to say is how the Higgs mechanism works, because people say, how does the Higgs boson give mass to every particle? That's actually why we're discovering it. In fact, that was the predominant reason why we're looking for it, something that explains how particles acquire their mass. So this is a cartoon actually that was, there was a contest in the UK Parliament because the British were funding physicists and funding them looking for the Higgs boson, and they wanted an easy explanation of how the Higgs boson works that even legislatures can understand. And in fact, there was a person in the collaboration that I worked on that won a case of champagne that we enjoyed later after he brought it back to the lab. So this is just an analogy how particles acquire their mass. So just picture a room full of physicists at a cocktail party, and they're just chatting amongst themselves. This is like what we call the Higgs field, something that permeates all space is a Higgs field. And then Einstein shows up, and there's a bar over on this side of the room, and Einstein's just really thirsty. He just wants to get himself a beer, and he starts making his way through the crowd. But the problem is that he's so well known that everybody, wants to get his autograph, explain their new theory to him. And what happens, he acquires inertia. It's harder for him to get the beer because people are interacting with him so heavily. They're crowding around. So he's acquired inertia, and inertia is essentially what mass is. The larger the mass, the more inertia you have. So this increases that resistance. So it's just like a particle moving through the Higgs field. And if it interacts strongly with the Higgs field, that means it's a massive particle. So Einstein is equivalent, those 6 quarks, the top quark is the heaviest quark. He's like the top quark of the physicist cocktail party circuit. If a first-year grad student, was here and wanted to get himself a beer, he can easily just walk through the room. People, you might have one friend that talks to him. He has very, very low mass because he doesn't interact very strongly with this Higgs field. And so that's equivalent of, say, of an electron compared to Einstein. Now, this is actually a nice analogy, but actually the analogy is great because it actually describes the Higgs boson as a particle itself. This only describes the field. And it's if you think, for people that have some interest in physics, if you think this sounds like ether, it kind of is. It's like a high-end ether. Now, to carry that analogy further, say a waiter was here and he sees Einstein walking down the hallway and he whispers, this guy right here, this was here, Einstein's coming. And what happens, that rumor itself spreads through the room, and it's like a collective action. And the mass of the Higgs boson, and the Higgs boson essentially is that collective motion through the room, and its mass is driven by how much the Higgs field interacts with itself. If these physicists know each other really, really well, it's like a big clump of collective action. That's the equivalent of a high mass. And if they don't know each other, just 3 or 4 people talking to each other, that'd be a low mass Higgs boson. So that describes actually what a Higgs boson is. It's the self-coupling that results in an observable particle in the Higgs field itself. As for describing this asymmetry, the Higgs boson has CP properties. We've measured them, not with great precision yet, but again, it behaves exactly like the standard model says it should. Now that we know its mass, once the mass is determined, essentially all the properties of the Higgs boson are determined. Every time we do an observation, it agrees with those properties, at least to the precision of the measurement that we make. So as far as we can see, this looks like the only Higgs boson. If there's multiple Higgs bosons, there might be, really massive ones. But as far as we can see, this is the Higgs boson described with the standard model, and it doesn't look like it's explaining the CP asymmetry. So that was a longer explanation, but hopefully that helps.
Excellent. Thanks, Rick. So at the moment, we don't have any more questions from the audience, but I have one question. So, there's all of these quarks that are named charm and strange and bottom and up. And so I'd like you to tell me a little bit more about who names these things and where these names come from.
Yeah. The word quark was from James Joyce of actually 3 quarks for Master Mark. It was just a nonsensical name, so that's where quarks came from. And then the other particles are essentially just physicists choosing fanciful names. Up and down were pretty obvious. And in fact, the fact that they're kind of coupled makes sense, because they're actually 3 families of generations of particles. Up and down are one family, charm and strange is one, and then top and bottom, or truth and beauty, or T and B is the 3rd generation. And again, I work, a lot of my research had to do with particles containing the B quark. So I have what I think was the most entertaining title of a thesis of one of my grad students was a woman that measured the lifetime of the B sub C meson, which is a B quark and an anti-charm quark. And it was measuring the lifetime of a beautifully charming meson.
Excellent.
Yeah.
Well done.
So you can riff on those names. So it's just like that's the physicists that come up with the names.
So we have a question in the chat or in the Q&A. Was it strange, the first new one from the who ordered that of the J/PSI? And
oh, that's a good point. No, actually, the J psi is a charm quark and an anti-charm quark, and that was it's called the November Revolution. That was actually the 4th quark. Is that the strange quarks? Why they're called strange quarks? Because they are in particles that acted strangely. That's what strange came from. And actually, they observed that in cosmic rays, cosmic ray collisions, and also just like in the olden days when they had bubble chambers, they actually particles that lived a long time and then decayed could only be explained by a strange quark. But it's sort of like they didn't wrap it up until they had 4 quarks that fit into a system that explained everything. And then actually the standard model was built out of the 4 quarks, but then it easily extended to the top and bottom quark.
Excellent. Great. So somebody asked a little bit of a different question, but I think it's really appropriate for this forum. How does your research relate to your work as Executive Dean of the College of Arts and Sciences?
Oh, man. That's not great. Well, it's actually, no, what actually it did is that these are gigantic international collaborations. So like when I was a grad student, it was about 150 people, 150 physicists in a collaboration. When I was essentially a postdoc research scientist over at CERN, the European lab, The experiment was like 350, 400. And then when at Fermilab, it was like 550, 600 physicists. Now that Atlas collaboration, that gigantic detector, that's like 2,000 physicists. When you work in these big collaborations, it's complexity. So it's actually, they're big and complicated. It was easier because all physicists speak the same language. It's a little bit easier, but you have to have a lot of organization to actually run these collaborations and run them smoothly. And actually I was an appointed or elected physics coordinator for a number of times. And there, what you're doing is that you're using the resources of the experiment, not to teach, but essentially you're saying this group gets this many computer cycles, this group can run a calibration run, this group can look at the certain aspect of the data, like have 2 weeks of what we call a trigger to get special types of events, and just mapping out the physics. So it's actually, that was kind of related to these big experiments. What's great is actually working with such diverse groups of people from all around the world. And there's everybody, each country actually has their strengths in the physics that's being done. It's very enjoyable.
It would seem to me that, you go from the entire, you cross the entire spectrum, right? From what I might call ethereal, things you can't see, can't touch, to these huge experimental apparati that you have to build. There's massive amounts of engineering involved. So in some ways, it's a very practical thing because you're building these large facilities, right? Things that nobody's done before, yet you're measuring and talking about it, dealing with and understanding and comprehending things that are so ethereal that most people can't even get their head around them, and you can't even find a good name for them. So that's the entire spectrum, right? I mean, everybody in the College of Arts and Sciences has to fit in that window somewhere.
That's right. Well, Jeff, I think you explained it better than I did. Thank you very much.
I don't know about that. I'm just impressed by your ability to go from one end to the other. I usually find myself somewhere in the middle. So.
Yeah. Well, thank you very much for your attention, of everybody out there. Really appreciate it.
Thank you again for joining us and participating in this evening's live stream. I would like to thank Dean Van Kooten and Professor Zaleski for their time and expertise. We are grateful to you all. Finally, I should acknowledge that events like this would not be possible without the support of donors who understand the value of a liberal arts education. If you would like to support the faculty, students, and programs of the College of Arts and Sciences, please consider making a contribution to the Arts and Sciences Priority Fund at the Indiana University Foundation. Until next time, take care and stay safe.